a demo class. So I'm thinking of taking much celebrated topic in gas dynamics, that is isentropic relations. We have uh, uh, we have come across like this isentropic relations in many occasions. So I thought of taking that as a topic today. Um, so yeah, myself Akshay. So I'm tech research guy at IISc. So today's class, first I will quickly recap the thermodynamics basics, what we actually uh, understood from our basics of thermodynamics. So we know that enthalpy relation, so where H is a specific enthalpy. I suppose we are well aware of what is specific properties, right? Like any properties which is um, divided per unit mass. So that is called a specific properties. Like here, my enthalpy I'm representing as a small h. That is nothing but a enthalpy per unit mass. So that is a specific enthalpy. So this relation is enthalpy and internal energy and flow work. So this is a well-known relation in thermodynamics. We will take it as granted for now, as it is demo class. I am not going into the details of how we can arrive at this particular relation. Similarly, we have other relation, that is state relation. So this is also well-known relation. So that is P is equal to rho RT. So we know for any system. So if I have a coordinate system like x, y, z, right? X, y, and z axis. So if I want to find a position of a point, or any point, if I have to define it with respect to my coordinate system, so I will be having three respective positions, right? Like from the x-axis, how much is the distance, and from the y-axis, how much it is the distance, and from the z-axis, how much is the distance. So based on that, we will fix a position of a point. So similarly, in thermodynamics, we have a very unique coordinate system, I can say. It's just an analogy, so you should not take like this is coordinate systems kind of thing. So, but to define any state, like a state of a particle, so then what we will do is like we will define or fix with respect to P, rho, and T. So these are the three thermodynamic variables through which we can fix the position of a it is not a position, it is a state of a particle. So at what pressure it is, and at what temperature it is there, and what is the specific volume of that particular particle. So based on that, I can say the state of a particle. So this is a state relation. This is how the relation between P, rho, and T. So there is one more term which comes in, that is R. R is gas constant. So this is basically defined as Ru by M, where Ru is nothing but our universal gas constant. M is a molecular weight of a particular gas we are using, right? And we have one more relation, that is Cp minus Cv is equal to R. How this gas constant R is related with respect to specific constants. So Cp is nothing but specific heated constant pressure, whereas Cv is specific heated constant volume. So for any gas particle, this relation should hold good. It's irrespective of whether it is a perfect gas or calorically perfect gas or a thermally perfect gas. This relation should hold good as long as it's a perfect gas, right? So, and we can define a unique non-dimensional number called a Cp by Cv, but that is we call it as gamma, or gas constant. So Cp by Cv, that is the relation for gamma, but gamma is more related to a molecular um, idea of a particle, like whether it is a monatomic gas or diatomic gas or something like that. But that is not our interest, because all we do in our fluid mechanics or gas dynamics courses, we use a macroscopic approach. We don't use a microscopic approach. So we directly take gamma as a constant value. Okay. So this keeping these things in mind, like this is a very basic introduction to our thermodynamics. So keeping these things in mind, so now I am going to show you the isentropic relations, because these few relations what I've shown here are useful in the in arriving the relation for isentropic flow, right? So we also have laws of thermodynamics. The first law states that um, conservation of energy. So that means the change in internal energy is related to the change in work or change in heat transfer or change in work. So here we have to keep in mind that, so these symbols actually have a meaning. So you can see I used a delta over here, whereas I used d over here. This means this is a exact differential where I can represent the change in internal energy as E2 minus E1 form, whereas I cannot represent delta Q as Q2 minus Q1. This is wrong. This is not a path function. So sorry, it is not a point function. It's a path function. It depends on the path through which the process is taking place. So both work and heat are properties where they change across the boundaries. They are not internal. So they occurs in the boundary of a system. So if I have a system of my interest, say something is happening over here, work transfer and heat transfer are related to the system boundaries, right? Whereas internal energy is what taking place within the system. That is why we can represent it as a exact differential, or I can write in terms of a point function, right? So that is one important thing when it comes to a first law of thermodynamics, because we will use this relation, but we have to understand the meaning of the individual terms, right? Similarly, we have a concept of entropy that is given by second law of thermodynamics, right? So it's why we need a second law, that is a first question, because the first law of thermodynamics states that the conservation of energy, but it doesn't give you an idea about in which direction the work has to take place. Like if suppose I have a ice which is sitting on a hot plate, so we know for sure that the the heat will transfer from the hot plate to the ice, and ice will start melting. But the first law of thermodynamics can also say that the ice will cool the hot plate. That is not possible in physical sense, right? Like we know that whenever you keep ice on a hot plate, you know ice is going to melt. It is not the plate which is going to be like reverse, like keeping ice as same, but the plate is going to cool down. It is not like this. They will attain an equilibrium position, but the energy transfer has to come from one direction. So that is given by second law. So it states that the process will takes place such that the entropy of a system is going to increase. That is the second law of thermodynamics in nutshell. That is the second law of thermodynamics. We have a different statements for second law of thermodynamics. One is like Clausius inequality statement. So that is like we cannot have transfer from heat, that is from a cooler body to hotter body. That is not possible. So there are two famous statements to define a second law. One is Clausius inequality, other one is Planck's statements, right? So Kelvin Planck statement. So here we are taking how the entropy is related to uh, heat transfer. So that is nothing but the ds. That is nothing but, again, the ds in the sense, the moment when I have a d, that means I can represent it as a point function, that is s2 minus s1. It is equally valid, is equal to the reversible heat transfer to the temperature, the reference temperature of the system. So now again, I am not going into the details of what reversible process and irreversible process as far as this demo is concerned. But when we see in our actual classes, so we will be defining what is this process all about, right? So now um, this is a very basic statement for change in entropy. And if I account for irreversibilities in the flow, so then I can also have the change in entropy that is coming through a irreversible process. The irreversible process through which the entropy is changed, that means I cannot come back to a initial entropy value, whereas in a reversible process I can come back to an initial position or initial state. But once the flow goes through an irreversible process, I cannot come back. That's the meaning of irreversibility. So we cannot come back. That's the um, uh, meaning over here. So now for adiabatic process, because I am going to talk about now isentropic relation, so I have to introduce you a adiabatic process. The adiabatic process is nothing but a process in which a heat transfer is zero, so our heat transfer is absent. There is no heat transfer, right? So that means a dq becomes zero, so my ds is becomes greater than or equal to zero, depending on whether it is a reversible or irreversible. That's it. So to arrive at a isentropic relation, so we understood a basic concepts of all the thermodynamics ideas. So now I will quickly give you a expression, so through which I can arrive a isentropic relation. So that is nothing but ds is equal to delta q divided by t plus ds irreversible. So now if I take out that irreversibility out of the question, so that means like I am talking about isentropic process. Isentropic process is nothing but both adiabatic as well as reversible. So I am taking about the irreversibility effect out, because this is going to be zero for isentropic process. So that means I can write delta q is equal to t ds, right? So now I have my first law of thermodynamics that states that delta q plus delta w, which is equal to dE, or I can replace this one equally with TDS plus delta W is equal to dE. We also have a relation that is a flow work, that is nothing but delta W, which is equal to PdV. So if I replace that one, or minus PdV, it depends on the direction how you take. So minus PdV equal to dE, right? So again I have the relation between enthalpy and internal energy, that is E plus PV. H is equal to, if I take a differential of that one, so that is nothing but dE plus PdV plus VdP. So I can replace my dE from here, so that turns out to be dH minus PdV minus VdP is equal to dE. So if I replace over here, so that becomes dH minus PdV minus VdP equal to TDS minus PdV. So this get cancels. I will end up with TDS is equal to DH minus VdP, right? So this is a very interesting equation. So now what we can do is, like, we know that enthalpy is a function of temperature. Similarly, internal energy is also a function of temperature. So H can be written in terms of CPT, where CP is constant, like specific heat at constant pressure. So if I use this one, so this means dH is equal to CP dt, because it's a constant, CP is constant. So my TDS relation now looks like TDS is equal to CP dt minus VdP. That's what we have, right? So this is one important relation through which I can derive isentropic quantities. So you see here, if I integrate this equation from ds is equal to 0.1 to 2. The process is taking place between 0.1 to 2. Then integration of 1 to 2 Cp dt divided by T minus integration of 0.1 to 2 Vdp divided by T. So we know from our state relation P is equal to rho RT, or I can write that rho is nothing but 1 by specific volume. So or PV is equal to RT, or I can write V by T is equal to R by P. So if I do that one, so I can substitute over here. So this becomes ds integrated is equal to Cp is constant, I can take outside, dt by T minus R is constant, I can take outside. So 1 to 2 dp by P. So this is very straightforward integration. So I can integrate directly. So that gives me S2 minus S1. Yeah, here we have S2 minus S1 is equal to Cp ln of T2 by T1 minus R ln of P2 by P1. This is a very famous isentropic relation. And if I have for isentropic process, that means S2 is equal to S1. The entropy is going to be constant. That's the meaning of isentropic. So this term becomes 0, equal to Cp ln T2 by T1 minus R ln P2 by P1. So if I rearrange this term, that becomes P2 by T1 to the power of Cp by R should be equal to P2 by P1. Right? So now I know Cp minus Cv is equal to R, or if I take this one, Cp by Cv minus 1 is equal to R by Cv, or that becomes gamma minus 1 is equal to R by Cv, or similarly if I divide it by Cp, that becomes 1 minus 1 by gamma is equal to R by Cp, or I can write Cp by R is equal to Cp by R is equal to gamma by gamma minus 1, right? So this becomes P2 by P1 is equal to T2 by T1 to the power of gamma by gamma minus 1. So similarly, I can also arrive at a relation for a density change, that is a rho 2 by rho 1 in terms of the T2 by T1 T2 by T1 to the power of 1 by gamma minus 1. So this for the time being, I'm not showing how we can arrive at this relation, but we can arrive. That is again coming from TDS relation only. I can have a TDS relation which is equal to dE plus PdV. So from here I can actually get into, because dE can be represented in terms of CVDT. So just we are using this idea to arrive at rho 2 by rho 1 form, right? So what we have arrived is I can have a single isentropic relation, that is nothing but T2 by T1 is equal to P2 by P1 to the power of gamma minus 1 by gamma, which is also equal to rho 2 by rho 1 to the power of gamma minus 1. So this is very important relation for isentropic flows, because this helps you a lot in solving different numericals, right? So I think you guys have any questions so far? I cannot see your chat. If you have a question, you can unmute and ask yourself. Okay, if you have no questions, so we can take up this a problem which is being asked in 2018 GATE paper. This is very interesting question. So they're given the relation, they're asking the relation between the pressure P and velocity V for a steady isentropic flow at 2 points along a streamline is, with a C is constant. Here you see, I have a streamline and flow is going through a isentropic process along a streamline. So I have a point 1 and I have a point 2 within the streamline, where the properties are defined like P1 V1 over here, whereas here I have pressure and velocity P2 V2, right? If this is a isentropic process, what should be the relation? Which of this relation is true? That is what they are asking, right? So I can have a energy equation for this flow process, that is H1 plus V1 square by 2 equal to H2 plus V2 square by 2. So if it is an isentropic process, then this relation should hold good. That means which is equal to constant or equal to H naught. That is a stagnation enthalpy, right? So this is constant. So I am using this idea over here to arrive at the relation. So see here. So once I have that kind of a relation, so I can write V1 square by 2 minus V2 square by 2 equal to H2 minus H1. So or else I can also write like Cp T2 minus T1, right? Or I can also write in terms of, if I take a T1 common, so that becomes Cp T1 times, or what I do is I will take T2 common instead of T1. So that becomes 1 minus T1 by T2, right? So now I know for an isentropic flow, I can represent T1 by T2 in terms of pressure ratio. That is nothing but Cp T2, because all we need, like if you look at all the options available, they are relating pressure and velocity. So somehow I have to bring into the form that the relation looks like the pressure and velocity relation. So that's what I am trying to do here. So this T1 by T2 form I am writing in terms of P1 by P2 to the power of gamma minus 1 by gamma, right? Now also for isentropic relation, I know PV to the power of gamma is equal to constant, right? So if I use this idea, so that becomes P1 V1 to the power of gamma is equal to P2 V2 to the power of gamma, that is equal to constant C, right? So that means I can write this T2 in terms of, again, pressure and yeah, I can write in terms of pressure, because Cp is nothing but gamma R divided by gamma minus 1 times T2, 1 minus this term remains same, P1 by P2 to the power of gamma minus 1 by gamma. So what is R times T2? If I have a P is equal to rho RT, that means RT is equal to P by rho. So what I'm doing over here is like gamma R T2 divided by gamma minus 1. If I take P2 outside, that is 1 by P2 to the power of gamma minus 1 by gamma, that is also equal to P2 to the power of gamma minus 1 by gamma minus P1 to the power of gamma minus 1 by gamma. All I am doing is like I am taking LCM. So I know RT2 is nothing but I can write in terms of P by rho. So I'm just taking this term here so that our calculations looks easy. So I can write RT2 is equal to P2 by rho 2. So if I replace over here, so that becomes P2 by rho 2 times 1 divided by P2 to the power of gamma minus 1 by gamma. So now I have P2 to the power of 1 and P2 to the power of gamma minus 1 by gamma. So that becomes P2 to the power of 1 minus gamma minus 1 by gamma. So if I take LCM over here, so that becomes gamma get cancelled. So that becomes 1 by gamma, right? So that becomes P2 to the power of minus 1 by gamma divided by rho 2. So I can replace over here. So that is nothing but gamma by gamma minus 1 times P2 to the power of minus 1 by gamma whole divided by rho 2 times P2 power gamma minus 1 by gamma minus P1 power gamma minus 1 by gamma, right? So now the interesting question is P2 power 1 minus gamma divided by rho 2. So if I look at this equation, the isentropic relation, that is nothing but P by rho to the power of gamma is equal to constant, or I can also write this part like P is equal to C times rho to the power of gamma, or if I take the gamma other side, that becomes P to the power of 1 by gamma, which is equal to constant to the power of something times rho, or the constant to the power of something is again constant. So that becomes rho is equal to constant times P to the power of 1 by gamma, or P to the power of 1 by gamma times rho is equal to constant. So we have the similar form over here. So I can treat all these terms to be gamma is constant, all these terms to be a constant times P2 to the power of gamma minus 1 by gamma minus P1 to the power of gamma minus 1 by gamma. So now the question is, so if I look back that one, the left hand side is V1 square by 2 minus V2 square by 2. The right hand side is some constant times this one. So if I look back the given options, which of these options is correct now? I have some, yes. So this is what we arrived, P1 to the power of gamma minus 1 by gamma, which is equal to V1 square by 2 minus V2 square by 2. The option C should be correct, right? But look over here. If I have to do this question completely, I have to go through um, lengthy algebraic manipulations, because we cannot arrive at the given form so easily. But there is a hint. There is a hint. So we don't have to do all these steps to decide which of these options is correct, because we know for a reason I have P2 by P1, which is equal to T2 by T1 to the power of gamma minus 1 by gamma, sorry, gamma by gamma minus 1, or The moment when I arrive at this equation, the energy equation, the next step I am going to get T1 by T2 form. So there only I can, so all I have to represent is T2 by T1 in terms of P2 by P1. So that becomes gamma minus 1 by gamma. The moment when you see which of these options are there in the like which of the options consist of this form of gamma minus 1 by gamma exponent, you can tick that answer correct, because obviously at the end of the day you are going to get this form only. This is the hint over there. The only confusion you guys can make is between gamma minus 1 by gamma or gamma by gamma minus 1. So you have to be careful. That is where your isentropic relation helps. So you can, this is like 1 minute question if you know the trick, or else it will take 3 to 4 minutes to get the correct answer. But still you can get the answer. So that is important, right? So I'll take one more question on isentropic relation. I guess like you guys can do this question. So I am just giving gamma is equal to 1.4. That is not given in the question. So I am just giving you gamma as 1.4. So can anybody tell me the answer? Okay, so let us solve it. So we have a rocket chamber, and from there the flow is going to expand in a nozzle. So here I have P naught and T naught in the chamber, and it is going to expand to PE and TE at the exit, right? So they are given that the chamber temperature T naught is 3000 Kelvin, the chamber pressure P naught is 100 bar, and the ambient pressure PE is 1 bar. They are asking what is the exit static temperature. That means what is this temperature value at the exit. So if they are also given, assume the flow in the nozzle is isentropic. So that means between, so if I take any streamline of the flow field, so I know for a reason, so this is going to be an isentropic process. So I can apply a isentropic relation between the point 1 that is in the chamber, the point 2 that is the exit plane. So that is nothing but P naught by PE to the power of gamma minus 1 by gamma, which is equal to T naught by TE. So I can apply this isentropic relation between this point to this point. So all I have to calculate is TE. So TE is equal to T naught times PE by P naught to the power of gamma minus 1 by gamma. So does anybody has an answer? Okay. So once you calculate this one, so you will end up with T naught is 3000 times TE is 1 divided by P naught is 100 to the power of 0.4 divided by 1.4. So if you do the calculation, you will end up with
805.
5. Yes, 805 Kelvin, right? So I guess like this is what I wanted to discuss for this demo class. So if you guys have any question, you guys can ask now. You see, like whatever we discussed in today's class, the thermodynamics and other things, like uh, it has to be discussed before when we start the isentropic relation, because uh, we should be able to understand what is there in basics of thermodynamics before understanding the isentropic relation, or else it becomes much more difficult to understand what's going on. In our actual class, like what we do is, like first we will start up with the understanding the basics of thermodynamics, and like covering the first law of thermodynamics and the other thermodynamic relations in detail before going into the isentropic relation itself. And then we will go on to see the isentropic relations before moving on to the um, shock waves and all. Isentropic relation is very important part of the gas dynamics. Yes. So is there anybody having a doubt?
No, sir.
Yeah. Good. I think Dinesh sir, you can take on from here. Yeah, I think like while we are waiting, so like if you guys have any general doubt, like you guys can ask here. Uh, I think Venkatesh, he's asking like how many marks do we need to get a good rank? Okay, so gate is like if you want to get into a good uh, college for MTech, so you should end up with good score. It is not exactly the rank which matters; it's the score it matters. Like if you guys are able to score more than 800 plus, like the chances to get into a better like options for MTech is more like IAC or IIT Madras, like they are highly competitive for to get into an MTech. So you have to target for a good score. So rank will come along with the score. Okay. And you know the gate is relative, right? So like it is not like you are scoring something, you are getting highest marks or something. So it is relative, the depending on the highest marks obtained on a particular gate paper, and to the average score whoever obtained in the gate papers. So based on that, the relative grading will be there to give you a score. So you have to target for good score.
Guys, so I think Sarah is done. So any concern you guys can write in chat in group. Okay. So I think we'll end meeting. Okay. I got some work.